All right, so our conversation today is now going to relate to kind of the causes of circular motion, why circular motion occurs, and some other types of concepts. So going back to our rotating object in a circle, so there's our rotating object in a circle. If this object is not moving in a straight line, then that means there must be a net force. Newton's first law says that, because objects with no net force move in straight lines at constant speeds. So if it's not moving in a straight line, then there must be a net force. So if an object is moving in a circle, there must be a net force. And you can reference Newton's first law for that. Now, what's responsible for that net force is different in every situation. Just like any other linear situation, your net force can be a single force or a combination of forces. Well, let's think about that example that we just looked at. So we had the ball moving in a circle at some radius. Let's assume it was rigid. It wasn't quite rigid. Let's assume it was moving at a constant speed. And then basically, if we were to think about what's going on here, if it was moving at a constant speed, that speed would be constant as it moves around the circle. It would just be constantly changing directions. So because my velocity vector is constantly changing directions, there must be acceleration, because I'm not in a straight line. My velocity vector is changing directions. So even though my speed is constant, the direction is changing. That's another reason why there must be a net force. So we can look at it from different perspectives. This perspective will help relate to acceleration. We're going to look kind of at forces first, because it makes a little bit more sense. So what forces are acting on this ball as it moves around the circle? Well, let's take a look at a side view, because that's easier. So this was a top view, and this is a side view. So here's the ball here, and here's the string. What I have is, from the side view, is, well, gravity's pulling it downwards. It was on the surface, and it wasn't hopping up or down off of the surface, hopefully. So I have a normal force, and that normal force is equal to my gravitational force. So in the y direction, my normal force minus my gravitational force has to be 0. And then what was responsible for it going around the circle? Well, there was tension in the string. So there is a tension force. So in the x direction, that is going to be my tension force. And actually, if you were to look at any point along that, my tension force actually always points towards the center of the circle. So from this top view, my tension force here always points towards the center. No matter where it is, it's constantly changing directions, but it's always pointed towards the center. So if I think about this, okay, there must be a net force. Well, my net force in this case is my force in the x direction. So this is my net force. And because we're talking about circular motion, we actually further define this net force, because it is responsible. This net force was responsible for the circular motion. We call that force the centripetal force. Which is not the same thing as the centrifugal force, which is imaginary. The centrifugal force is described as an outward pointing force that is responsible for causing objects to move in an outward direction. But those forces don't actually exist. For example, if this string were to be cut, at this point, this object would continue moving in a straight line from inertia and momentum, which are not forces. but it was a tension force, which was a center pointing force that was responsible for the circular motion. So I spend a lot of time studying centrifugal forces in atmospheric science because the Coriolis force is a centrifugal force, but it's also an imaginary force. It is needed to explain motion when you're in a non-inertial reference frame. So this doesn't exist. So never, ever, ever use centrifugal force. Okay, it's not a thing. Doesn't exist. Not for what we're doing here, because we're always looking at an inertial reference frame. So we're looking at our centripetal force here. So centripetal, by the way, means center seeking. So the centripetal force is our center seeking force, and it is a net force. In this case, it's equal to the tension force, which is an example of a single force being responsible for the motion. So the centripetal force is the net force directed towards the center, but it doesn't have to be composed of forces pointing directly towards the center, because its mathematical definition would be the sum of the radial forces acting on an object. So it's the sum of the radial forces acting on an object. So there's tangential and there's radial. So basically this is directed along the radius. It doesn't say directed towards the center. It says directed along the radius. So there are cases where your centripetal force is a combination of forces, and that combination of forces may or may not be directed inwards towards the center of the circle. So now I'm going to look at an example. And we're going to look at an example of if that ball was swung in a vertical circle. So a vertical circle would mean this is the ground, and we are looking at a side view. So that ball can be here. This is the string horizontal to the ground. We could have the string vertical to the ground, horizontal again, and vertical. Let's assume we're moving this way around the circle. We can assume that we have some method of keeping our velocity constant. Maybe it's being swung by some sort of rotary machine that can keep a constant, that can actually adjust the rate at which it's rotating to kind of counteract gravity and things. Or you can consider this to be a non-uniform situation where it could be speeding up or slowing down. At this point in time, we don't care what's actually happening to the speed. There just is a speed. So if we were to look at the forces of the different places, let's start off over here on the side. So we definitely have gravity pulling down and tension. And those are our only two forces because we're going to assume that there's no air resistance or anything going on. Well, our definition of centripetal force is the sum of the radial forces acting on an object. Well, my gravitational force is tangent to my radius. My tension force is directed along the radius. So therefore, my centripetal force, oh, by the way, we use the symbol capital F sub C as our centripetal force. So by definition, my centripetal force would be tension. Now here's something interesting. I do not draw an arrow for centripetal force ever on my diagram, because it is a net force. I don't draw the net force vector on my free body diagram, so I don't draw a centripetal force because it is a net force. So my centripetal force is a net force, and therefore it does not go on the diagram. Tension is what's responsible for the centripetal force at that point, so it is on the diagram. All right, well, let's look at the top. Well, at the top, gravity's still pulling me down, but now tension, which is always directed along the string, is pointing down. So what is my centripetal force? Well, it's the sum of the radial forces acting on an object. So, well, both gravity and tension are directed towards the center, so that means my centripetal force is equal to gravity plus tension. It's equal to the sum of those. So I have two different forces that are accounting it. So that's a combination of forces. Well, let's keep moving around the circle. Let's go back over to this point. Well, I'm going to have gravity pointing down. I'll have tension pointing towards the center. So this is really just the reverse of this case. So my centripetal force in this case is equal to my tension force. Okay, well, let's keep moving around the circle. Well, if I keep moving around the circle, I would get to the bottom. Well, gravity points down, but my tension points up. Well, I've defined essentially here that the inward direction is positive. So that means the outward direction is negative. So this gravitational force is still a radial force. It's still contributing to my centripetal force, but my centripetal force is going to be tension minus my gravitational force. Now, in order to move in a circle, your centripetal force must be positive. It must be directed towards the center. So that means that my tension force here has to be larger than gravity to go around the circle. And the bigger and bigger my tension is compared to gravity, the bigger and bigger my centripetal force will be. So my tension force here has to be larger than gravity in order to go around the circle. That's going to be important. Anytime you have these forces pointing in two directions, your centripetal force must point towards the center to go in the circle. It cannot be zero. If you're at zero, it goes in a straight line. So it's going to continue around the circle, then my tension force must be bigger than gravity. So in this example, you can see that my centripetal force changes as to what actually composes the force. Even if this was moving at a constant speed, then its acceleration would be constant in magnitude, and I'd have to have a constant net force if my acceleration was constant. So even if the value of centripetal force is constant or not constant, what constitutes it changes over the path of the motion. So that kind of gives you a little bit of a feel for centripetal force. One of the hardest things you're going to have to do this unit is to determine what is the centripetal force, what is the sum of the forces, which involves drawing a free body diagram separating out tangential and radial forces. Well, what if I wasn't at one of these nice simple spots? Now, you probably won't see that very often, but let's say I was at this spot here. Well, gravity would point straight down and tension would be pointing towards the center. I run into a problem. Gravity is not tangent to my circle. It has a radial component. And if I were to actually, therefore, rotate my axes so that I am either tangent to the circle or radial to the circle, what I would have to do is I would have to actually resolve that gravitational force into components. I would have a tangential component of gravity and a radial component of gravity. So that would be Fg tangent and Fg radial. So in this case, my centripetal force would be Ft plus Fg radial. So I'd have to figure out, well, what is that angle in order to resolve that? And that would be really hard, unless they gave you the angle that it was at that position. But so just realize every other point in there, in between these spots, is also going to have some combination of gravity and tension as your centripetal forces. It's only these 2 points on the end where it's just tension responsible for the centripetal force. So our centripetal force, because it is a net force, would be mass times acceleration. But in this case, if I have a centripetal force, that means that my acceleration must also be centripetal, because my force and my acceleration are vectors, mass is a scalar. So if I have a centripetal force, then my acceleration must be in the same direction. So the AC is a new variable. It is now our centripetal acceleration. It is a linear acceleration. So it has units of radians per second squared. And it is the linear acceleration directed in the direction of it's center seeking, so it will be directed towards the center. And it can be calculated. Now, through experimentation, they've determined that centripetal acceleration in magnitude is equal to the tangential speed squared divided by the radius. This is the mathematical definition of centripetal acceleration. So if I know what my linear speed is, and I know what my radius is, I can calculate the magnitude of my centripetal acceleration. It's really important to realize that my centripetal acceleration is proportional to my tangential speed squared. So if I were to double my tangential speed, I would quadruple my acceleration. And my centripetal acceleration is proportional to 1 over the radius. So if I were to double the radius, I have the centripetal acceleration. So you can use that centripetal acceleration equation to sub in. So I can sub in centripetal acceleration on this side of the equation. I can use net force equations to sub it on this side. And then I can use the forces that I know, and I can use my speed and radius values to kind of solve for different things. I can also do this in rotational terms. So remember, you're going to have some sort of angular speed associated with that. And remember that our tangential speed is equal to r times omega. So my centripetal acceleration is going to be r omega squared over r, which is going to be r squared omega squared over r, and one of the r's cancels. So you get that AC is equal to r omega squared as another option, where omega is your angular velocity squared. And once again, if you look at kind of the units of this, this would be meters times radians squared per second squared. The radian squared cancels, so you're just left with meters per second squared. So this is a linear acceleration. You can do that up here with those variables as well. Now, we've now talked about two different accelerations. We've talked about a centripetal acceleration, and we've talked about a tangential acceleration. So we have our centripetal acceleration, which is vt squared over r, which is also equal to r omega squared. We also have a tangential acceleration, which is the change in the tangential velocity over time, which is also equal to r times alpha. So we have two separate linear accelerations. Well, the centripetal acceleration is pointed towards the center of the circle, by definition. So if I'm moving in a circle, my centripetal acceleration always points towards the center. My tangential acceleration always points tangent to the circle. If I'm moving in this direction, if my AT is pointed in the same direction, I'm speeding up. I could have my AT pointed in the opposite direction, I'd be slowing down. When I talk about just acceleration, so we have centripetal acceleration, tangential acceleration. If I just ask for acceleration, no subscripts, what am I talking about? Well, that is my linear acceleration. It is the vector sum of centripetal acceleration and tangential acceleration. So if I were, say, to take AC and AT and do vector addition, my linear acceleration vector would point as a vector sum between those two. So you would only have a tangential acceleration if you are speeding up or slowing, if you're changing speeds around the circle. It is responsible for changing speeds around the circle. The centripetal acceleration is not responsible for changing speeds. It is responsible for changing directions. So if you're moving at a constant speed around the circle, you have only centripetal acceleration. If you are changing speeds, whether speeding up or slowing down, you will have both a centripetal acceleration and a tangential acceleration. So when we talk about uniform circular motion, and you'll see this, an object moves uniformly. All right, so if we want to define uniform circular motion, which sometimes you'll see abbreviated as UCM. What does that mean? Uniform circular motion is the special case when you have constant values. Your constant values would be your centripetal acceleration is constant, your tangential speed is constant, it would mean that your omega is constant. If your centripetal acceleration is constant, you're not changing mass, your centripetal force would be constant. What it also means is it means that your tangential acceleration is equal to 0. You cannot be speeding up or slowing down around the circle, which also means that your alpha has to be 0. We also assume throughout all of this that we're rigid. So that means that you have a constant radius. So when you see that uniform circular motion, those are the assumptions that we're making. So if our centripetal force is constant, that just means we're going at constant speed. That doesn't mean if I'm going in a circle, my centripetal force is always made up of the same variables. All right, so I hope that gives you a feel for circular motion.